Yes, dear students, last class we are discussed about the single block break. Okay, today in this class we'll go for a band break. Before going to this second type band break, we'll just have a we'll recall what exactly the single block break. Then we'll come to know what the difference between band break as well as the block break. Okay, in the block break or shoe break, you're seeing this shoe. Okay, whenever you apply the force like this, and this shoe or block uh, is going to move toward this direction, and it is going to stop this drum. So this is what happens, and the vehicle is going to stop, or any you can able to, this is called the brake, or it's called the block brake or shoe brake. Okay, whereas in the band brake there are two types. One is simple band brake, other is differential band brake. First we'll go this first type, simple band brake. Okay, in this is the arrangement of the simple band brake. This is a fulcrum point, then this is a lever, and this is a drum. Whereas around this drum you can see the band or a belt kind of thing. Similarly, you can the similar arrangement where you can see the belt race, where it is flat belt or V belt which is surrounded on the pulley. Similarly, like this is a drum, and this is the band or belt kind of thing. Okay, whereas here, if this is a fulcrum and this is a lever, whenever you apply the brake force or you apply the pedal, this lever is going to lift like this, move like this, so that what happens, this band will go into, this band is going to push, or is going to, it will come into close contact with this drum, so that this rotating drum will going to stop. Then you're going to, the vehicle will stop. This is the one. When this is the arrangement, similarly to the block brake, here also this is a fulcrum point, this is called, where it is called O, and this is a force, uh, and distance between this point and this point is called A, and this point and this point is called B. Okay, if the wheel or drum rotating in the clockwise direction, this becomes T1, that is tight side, and this becomes the slack side. Okay, when it is in clockwise direction, when it is in clockwise direction, you can, let us see some terminology here. O is the pivot point or fulcrum point, theta is the angle of wrap, and mu is the coefficient of friction between this band as well as the drum. Okay, P is the power, R is the, or D is the diameter or radius of this drum. Okay, if sometimes in some questions there will be called RE. What is that RE? It is called effective radius. If the radius from this point to this point, that is including the belt thickness, then it is called effective radius. Sometimes it will not be, sometimes this real thickness of the belt is not given in the question, then you have to consider only the drum radius or drum diameter. Considering the band or belt thickness, then that is called RE or effective radius. Okay, that you should keep in mind. Okay, when we see this diagram, we can able to recall the belt drives. So similarly, the same formula, something like, we know this formula in the belt drives we learned in the last semester, that is ratio of tensions, that is T1 by T2 is equal to e to the power of mu theta. We know this. Whereas braking torque, the braking torque is equal to T1 minus T2 into radius. Okay, so let us see here now what exactly you need to, in the design we need to, very important concept is that we need to find out the moments. So if the drum is rotating in the clockwise direction, if you take this point as fulcrum point is O center, if you take, it is a fulcrum point, force into distance F into A is equal to T1 into distance B. So that's what I written here. F is equal to T1 by A into B. If it is taken negative direction, sorry, counterclockwise direction, then F, if this drum is rotating in, If the drum is rotating in this direction, then F into A, T2 into B. So T2 into B. So this becomes the formula for force. Okay. Next, we'll go to the design steps. Okay. Once you know this, you can. This is a normal general procedure. Torque is the torque formula, 9.55 10 to the power 6 P into P divided by N Newton millimeter. Step 2, ratio of tension. This is a very well known formula, where mu will be around 0.3 to 0.4. Torque, braking torque, that is MB is equal to T1 minus T2 into R. This is R. And based on clockwise or anti-counterclockwise direction, as we seen from this diagram, whether clockwise direction or anti-clockwise direction, we'll use this formula. For clockwise T1, for counterclockwise T2. Right. Step 5, thickness of the band, H is equal to 0.005 times the D. Width is W is equal to T1 divided by H into sigma D. Usually sigma D will take it as a steel. We'll consider the material is steel. Then the value will be around 50 to 60 MPa. So that will be if sometime it's the question it is not given, we'll consider this value is 50 to 60. So from these formulas we'll get it from data handbook 19.80 and 19.161. Next, brake lever design. All these things related to force, moment, all these things. So when we come to the step 6, that is brake lever. Lever means this point, this line. If you do, because that lever is a simple, is straight line kind of thing, we'll consider that as a small beam kind of thing. So we'll take it. This is a well-known formula, MB by I is equal to sigma B into C. So we'll take this value C30, because that lever is made up of C30 steel. So we'll get this 117.68 MPa. This is standard value from data handbook. And I is equal to, this is a cross section, I is equal to moment of inertia, and C1 is equal to H1 by 2, H1 is equal to 2 times the B1. If it is not given, we consider this thing. So simply substitute these things. This is the things we need to find out for designing the simple band brake. Okay, hope you understood this. This comes under simple band brake.